Good morning. It is February 25th, our second winter day of the semester. Today we're going to talk about Chapter 5. Notice where we are in our course organizer. We're just eating up those days with winter days. We're almost 50-50. Hopefully we can avoid that before we're done. This week we're going to talk about lists and dictionaries and tuples, all of which are cool things in Python and have huge applications way beyond arrays and array lists or anything else that you've learned before, because they're fundamentally different and they're very widely used, much more so than arrays and array lists in some other languages. These are the primary building blocks of objects, data storage, structures. These are the cool things. And I wish we were getting to do this face to face, but we're not. So we're going to run through this chapter pretty quick. Some of you that have probably already looked at the PDF realize that it's not that long. It's a pretty succinct chapter. Really, it's just the difference between squiggly braces, parentheses, and square brackets with functions attached to each one of those. We've already seen how functions and methods attached to objects are differ depending on what we're using. And we'll see that we have those with tuples and with lists and with dictionaries. But first things first, you don't have any exams this week. It's just a lab uh, dealing with lists and dictionaries and tuples, and it'll be interesting. And I will be in the Big Blue Button at noon if you want to talk through things about Chapter 4 or Chapter 5. Let's go ahead and jump right on in. Fundamentals of Chapter 5, Lists and Dictionaries. All right, you notice they don't mention tuples right away. List is a sequence of data values of any types. Of any type. Remember that, contrary to other languages where you have an array of type int or array of type string or an array list that contains objects, a list can contain anything, a number, a string, a Boolean, whatever you want to stick in there. It's a storage place that's just like your grocery list. It's going to have, I actually compare it more to your grocery basket where it's going to contain meat and eggs and cereal and toilet paper, but they're all in the basket. That's a list. And then a dictionary is very much like a map in Java in that you have a value and I'm sorry, you have some sort of key, some sort of unique thing, and it has something attached to it. The simplest one would be days of the week, 1 through 7, where 1 contains Monday, 2 contains Tuesday, 3 contains Wednesday, so on, so on. Lists and dictionaries are the two most powerful. List is just a sequence of data values. It could be anything. It has a unique index. We do use indexes on list. 0 to the length of the list minus 1. So if your list has 10 things on it, you can get to it by using an index with square brackets, just like we've always done, from 0 through 9. There's not a index 10. It contains 10 elements, and those numbers are from 0 to 9. So remember that length minus 1 is always pointing at the last one in the list, and 0 is always the first one. Simple example, a couple of examples. One of them is just a collection of fruits. Notice they're all strings in single quotes. Got 3 elements in it. The valid indexes would be 0 for apples, 1 for oranges, 2 for cherries. The next one is a list of lists. It contains coordinates, basically. The first one in the list is another list that contains 5 and 9. The second one in the list is another list that contains 541 and 78. So if we did list 1, then we have a choice. This is 0, this is 1 inside that list. This is 0, this is 1 inside that list. Inside the bigger list, this is 0 and this is 1. Now, unlike some other language where you consider this like a multidimensional array, in Python, you would actually get this first element and store it in a list, and then you would just deal with that little list that you've created, and deal with 5 and 9. And then you would do it again on the bigger list. The cool thing about list was that things are stored in a list based off, could be their variable names, could be their value. In this particular case, we created this variable called x. We put x into a list. We also put this function, math square root of 2, in that list as well. The list, when you dump it out, like we're doing right here, shows the number 2 and the value that was generated by the expression. Notice what else we're doing. Hey, x plus 1, that's 2. We're creating a new list that contains 3. Square brackets create a list. Anything that's contained in it is going to generate something that could either be saved in a variable or not and exist in memory as a list of items. It's much simpler than some of the other languages with all that set up. Here's one where we're creating a list of things called first. Square brackets, 1, 2, 3, 4. That gets stored first as pointing at the memory location where 1 starts. Next, we're creating another one using the range. It's going to give us the exact same values. We're using range. Start with 1, go up through 5. Remember how we do that? 5 minus 1, that gives us 4 numbers. 1, 2, 3, 4, because we're starting with 1. That creates the magic word list. Notice list uses open parentheses. Put inside the parentheses what you want to turn into a list, just like string or int or float or any of those other functions we've used. List creates a list. So now we've got these two lists. First, 1, 2, 3, 4. Second, 1, 2, 3, 4. Generated two completely different ways. And a list can be built from anything that's a sequence of characters. You can use range. You can define them yourself. You can give it a string, which is just a list of characters that happen to be next to each other. Notice it even puts the space in there because space is a valid character. And remember from last time, when we're talking about our for loops, now that we have something that's a list of things, we can use the for statement to walk through that list and handle them one at a time if we wanted to. Now, len, square brackets, plus, and equal, they work on lists just like a list is any other data type. All right, so if we're creating that len, remember our first from the previous slide? 1, 2, 3, 4. And we're saying, hey, how long are you? It's going to tell you I've got 4 elements in it. Remember, we're using indexes, so we're getting the first one using index 0, and that returns 1. We're also doing slices. We can take 7 of them. Start with the second index and go to 4 minus 2. Go for 2 characters. 0, 1, 2, 2 characters. 3 and 4. Going to cut it right off, just like we were doing string slicing last week. Concatenation, just like string slicing last week, which this is kind of leading into a string is basically a list full of characters. But that's part of the mutability of data that we were kind of messing with last week, and it continues on this week. You can use concatenation and equals for a comparison. Notice we've got this list, 1, 2, 3, 4, called first. We're just adding another list to it called 5, 6, and that creates a new list called 1, 2, 3, 4, 5, 6. If we want to compare one list to another one, this is going to work. Now we're fixing to have a whole slide where this doesn't work exactly like you'd expect, but most of the time it's good enough. Are these lists the same? And we're going to find that the same can be defined several different ways. If you want to print it, this is the way we would do it back in the day. Make a nice little string and it burps it out to the screen. We can also pass it a list. Notice the only difference, it burps this one out as a list, a structured thing. This print and this print are not the same. They can be treated the same programmatically, but print, remember, is kind of a string interpreter. What do you want to print out to the screen? It has all that formatting, escape sequences, things that can be added in. So print's going to do its own thing. If it sees a list, it's going to print it out with the square brackets separated by commas. If it sees us this way, which could be turned into a list, it's going to print it out just like that. Now, the other keyword that you need to know about is in. We can use in to see if something is in a list. 3 in 1, 2, 3 is going to return true because there's a 3, there's a 3. 0 in 1, 2, 3 is going to return false. Another expression that we could use in for loops or fors or anything else where we have to ask a true false question. Is this thing in the list? Keyword in. Lists are mutable. Lists are mutable. That means that it can change in place. In Java, it's one of the hard rules. Like a string is immutable. It can't change. And if you combine anything to it, you're actually creating a whole new thing, a whole new string. Python changes things in place if it's a list defined with the square brackets. You can insert stuff, you can remove stuff, you can replace things that are in places. Now, this is important. The list maintains its identity. In other words, it's the same list before, but the stuff that's inside it, called its state, its length, and its contents can change. You can use subscripts to change it. So we've got example that contains 1, 2, 3, 4. Notice the square brackets. We dump it out. There she blows. 1, 2, 3, 4. Now we say example 3, set that to 0. So we do our indexes are 0, 1, 2, 3. So we're changing this one right here. Set that to 0. Dump it out now. There you go. 4 has been changed to 0. You're using a subscript to find exactly in the list where you want to change something. All right, it's a target of an assignment. It's not the lists, but a single element within it once you use these square braces. Now, here's a simple one. We've got this thing, 2, 3, 4, 5. Dump it out. There it is, 2, 3, 4, 5. We're walking through it one at a time. And notice how we're using the for loop here. In range for the length of numbers. Len numbers is going to return 4. So we did range 4, which means we're getting 1, 1, 2, 3. That's the numbers that we get out of range. So the first time we say, hey, numbers, 0. Take whatever's at number 0, which is 2. Multiply it, square it by 2. And we assign that back into 0. Then we come and get 1. Numbers at 1, 3. Square it, put it back in there. 4. Square it, put it back in there. 5. Square it, put it back in there. Now when we dump out numbers, we've got these new values because we were referencing the index, the location. We were pulling that location out, squaring it, and putting it back in the same place. So we were overriding our list. Unlike some other languages, the list did not change. Numbers remained the same, but the values that were in it changed. Here's one that you can do it with sentences. And this probably would have been nice to know last week, right? Sentence, split the sentence. Now we're now at a list called words. Notice if we dump out words, we get a list, square brackets, that contains the words. Split by default, remember, is our common token, which is spaces. Splits all the spaces. For index and range length of words. In other words, range, 0, 1, 2, 3, 4. We're using that as an index to get to the first one, change it to upper. Second one, change it to upper. Third, change it to upper. Because remember, what's contained in words index is a string, and strings have an upper method or a lower method. You could go either way. Dump it out after the for loop completes. Everything's been capitalized. Now, with these lists, it comes with some default methods. Remember, upper is not attached to list. Upper is attached to string, and that's what the list element of a specific index contained. But when you're talking about the list itself, they've got 5 main methods that we use. Append adds a single thing. Extend adds another list. So you could say list1.extend list2, and it's going to stick it on the end, combine them. You can also insert things in a specific place in the list by telling it where do you want to insert it and what do you want to insert. All right. The cool thing about insert is insert's going to work. All right. It's going to work. Even if you do a dumber and give it some index that's way out in the boonies, it's just going to stick it on the end. An insert is good to use rather than concatenation sometimes because you can run into problems when you're concatenating and not quite for sure where you were. And especially if you try to access something without checking the length of a list first, you can get into a place where you're accessing no man's land. Whereas insert, it's just going to stick it on the end, even if you're lost. Now, pop and pop index, these are important because this word right here is very important in this definition. You took it out of the list. All right, if you do pop, it's going to take the last thing off of the list. The last thing, the highest index, is going to pop that right off, return it to you, and it's removed from the list. If you want to get a specific thing, you can tell it which one you want, which index. Notice it's going to remove it and return that back to you. But it's no longer in your list. And some people forget that. And then they go looking for something later and it's not there because they popped it off. Now, if you recognize this terminology, pop, it's actually from a data structure called stacks. It's like the old plates in the cafeteria. Remember where they have those big springs and they push the plates down on top of each other? And the last one that's put on that stack is the first one that you get off. And this is basically what's happening here. The last element in your list is going to get popped off and returned to you so that you can store it or use it or move on. Here's an example. Simple list, square brackets, 1, 2. There it is, example, dump it out. Now we insert at position 1 the number 10. Notice it moves 2 over, puts 10 where 2 was. Now the length of our thing is 3 instead of 2. Here's the insert where we're giving it basically an index that doesn't exist right now. Example insert 3. We don't have a 3. We have 0, 1, and 2. But it says, okay, whatever. It's bigger than the biggest one I already have, which is 2. So let's just stick it on the end. So our list ends up looking like this one here on the bottom. Now, append is a little different. Append always means to stick it on the end. And a append deals with a single element. Append deals with a single element. It's a good test question, by the way. Append 3 sticks it on the end. Append just means to stick it on the end. Extend is when you want to combine list. You use extend if you want to add another list to an existing list. It's going to add it to the end. You can also use concatenation. Because remember, these are just like strings to a certain extent. We got this list called example that has 1, 2, 3, 11, 12, 13, plus 14 and 15. There we go. Now, here's the weird part. And this is something you need to keep in mind. We used extend and append here, and that did change the value that was stored in example. When you use concatenation, this is like a temporary variable, and it existed for a second, 1, 2, 3, 11, 12, 13, 14, 15, and we could have assigned that to something else, but we didn't. So on the very next line, when you dump out example, it went back to the way it was before. Notice that when you use the functions append and extend, the variable contents itself was changed. When you use concatenation, it creates something that could be saved, but if you don't save it, it's just going to go away. So this was temporary. These are permanent. Like we were saying, pop pulls off the last element, whatever it is. If you give pop a parameter, like a 0 or a valid index, it's going to pull that one off exactly. But if you just use pop with open close parentheses, you're getting the last thing in the list. All right. Now, remember we talked about the keyword in earlier. determines an element's presence or absence, but it doesn't tell you where it was. It's just going to return true or false. That's what it does. And we've used it, in for loops. We've used it in other things so far. But now we can say if target in a list, that's going to return true or false. And if it's in there, we can print it out. Otherwise, we print out -1. All right. The deal is, if it's not in the list, it's going to raise an error. Now, remember, we've kind of mentioned raising errors. We're going to talk about more in the future. That doesn't always mean that your program explodes. It just means that you don't have anything in hand that you can actually use at this point. Because we ask a question. If target is in a list, then target's going to contain what we want, right? If it's not, then what do we have? We don't know where we were. We don't know where what we didn't find is. We don't know what was returned. So we need to print out something. In this case, we're asking a question, a true-false question. We put a print statement there to handle it. If we hadn't, we probably would have gotten an error message saying, hey, didn't find this element, is missing. But I want you to notice something interesting about this. I said, if target in list, I said, if the value 45 is in the list, if it is in the list, I said, hey, list, give me the index of the variable I'm looking for. Give me the index of 45. And print out whatever that is. So I said, hey, index 45, that's a 1. Print a list 1. And it's going to dump it out to the screen. Elements that are within a list can be used to search that list. And if you don't use the square brackets, notice there's no square bracket stuff going on here. I said alist.index function, pass it a value, it will return the index of that list. This will turn into 1. Print 1, 45. Very flexible. Python, very flexible. Now, we've just seen one method that's attached to a list. Well, we've actually seen several. We've got this list: append, extend, and insert, and pop. There's some examples of exert, extend, pop, all that stuff. We've also got this new one called index, where we can find the value in an index, the index of a value within a list by searching for the value. And that's kind of cool. That's something you can't do in most languages. We've got another one called sort. And sort operates on the list and doesn't have to be stored anywhere. In other words, that fourth line here, I've got this 42108, dump it out, there it is. This right here changes example without having to save it anywhere. In other words, it just did it internally. I didn't have to save it to a new list, didn't have to do anything like that. And it automatically sorts the list. Most of these, there's several of them that we're fixing to talk about, do not return a value. They operate on the list internally. And they cause its state to change, but you don't have to save that. It just happens. Sort is one of those. These are called mutator methods because they change the method without you having to save it anywhere. It's internal to the state of the object, whatever that list is. It's a type of object. All right. Inserting and appending and extending and popping and sorting usually return no value of interest to the caller. I mean, pop does, right? We've seen that one. Pop will give us back something, but insert doesn't, append doesn't, extend doesn't, sort doesn't. They don't return anything to us that's useful, that we could ask a question about, that we need to store anywhere. Pop's the only one that does. And these are called mutator. They all do return a method, a value, but that value is called none. And if you're ever running a program and all of a sudden you start getting none printing out on the screen, that usually means that you're trying to save something that doesn't need to be saved. This is a good example. I sorted a list, but then I saved it back into a list. And when I printed out, a list returned what a list sort turned into, which is the default value of none. Now that's important that you remember that almost every function that we call returns a value, but 99% of the time that value is none. We have things that do return values, exceptions like pop. We like pop. But we have insert, append, extend, sort that all do things that we don't really have to worry about it. It just gets done. We don't have to check it, sort it, do anything weird after that. So keep that in mind. Default return value for everything is none. And if you start getting none, then go back and look at your code and go, do I even need to do this? It's all fixed. All better. All right. You get some weird stuff going on. All right. First, 10, 20, 30. Got that in there. I assign first to second. These are actually called aliases now because second, I didn't create a new list. I just pointed it where first was pointing. So it looks like this over here on the right. They're both pointing to the same place. And if I change something in either one of them, they're both pointing to the same place. So I actually changed it in both of them. All right, they're the exact same object. Because remember, a list, just like an array or an object in another language, does not reside in first. First points to a memory location where that thing starts. And now second does as well. Those are called aliases. If you don't want aliases, and a lot of times you don't want this. This is not what you intended. You wanted two different lists. Because you could want to compare the first one to the second one to see what changed over time. But if you did it this way, it's the same list and they're always going to be equal. So let's do this. I created an empty list. For every element in first, remember first has three numbers in it, 10, 20, 30, append those to third. 10, 99, 30. I forgot about our change. 10, 99, 30. Third contains 10, 99, 30. I change first. So it's 10, 130. Notice third didn't change because I created third one piece at a time. I didn't point it to first. I created it new. This created a new reference, and then I filled it up with the values from first. I did not point it at first. So now they're two different things. When I first started, they did this. When this slide ends, they look like that. Two different values, two different lists. Okay. Now I was telling you we can use the equal sign to compare things, to say, hey, is this object the same as that object? But the problem is equal is kind of stupid because if they contain the same values, say like these two, first and third, it's actually going to say that those are equal too because they contain the same stuff. But they're not the same object. So we got to define two different things here. We've got object identity. Are they the same object? And then we've got structural equivalence. Are they contain the same thing? Object identity checks to see if they're aliases for the same object. Structural equivalence is, do they have the same values in them? Like these two. These are structurally equivalent, but they're not the same object. All right. And the equal is kind of dumb. It doesn't have a way to tell the difference between, if either one of these are true, equal is going to return true. So is the keyword that differentiates between the two. If we use equal, let's see what happens here. First, 20, 30, 40. Second is pointing to first. Those are obviously aliases over here. Third is equal to first turned into a list, or you could use first with a blind slice like that from beginning to end and stuck in third. That's a whole different thing. That was created new. First equal to second, that's true. First is equal to third, that's true. Because remember, equal is stupid. Can't tell the difference between different objects, or are the variables the same? And in this case, the variables in contents are the same. It's all good. First is second. Those are pointing at the same object. First is third. Those are not. All right. So as a general rule, when you're comparing the contents of variables or the contents of lists, you're going to do it one by one and go check for structural integrity. Uh, this is kind of where you get yourself out of a bind. Think about when you're playing Doom, everything on the screen is a sprite. But it's kind of important to know the difference between is one of them a wall and is one of them a bullet. All right, are we pointing to a wall or a bullet? Which one's which? Am I pointing to different objects? Is going to come really into play a lot in gaming. Are they the same object or are they different objects? But you can use this equivalence most of the time. Just remember, equal is dumb. Okay, take a look at this code for just a minute. Basically, we're trying to find the median. You know, the common man's word is average of a set of numbers that come from a file name. And this is a good one to remember how to open a file name. Let's see. File name equal, we're entering a file name. We're assuming this file contains a bunch of numbers. So here we go. Open the file name, read only. There's our numbers list for line in F. And remember, this for actually reads the file, right? Get you a line. We're taking that line and we're splitting it into a list called words. So we now have that got created that contains a bunch of words. For each word that you find in words, append to word, turn it into a float, stick it in numbers. In other words, we're reading this like it's text because that's what open does. That's what read does. Returns a string. We're taking each one of these and then we're just appending it to numbers and converting each thing that we find into a number. So numbers at the end is going to end up with, 75, 21, 12, 2, 7, 5. In other words, we read this as a big long string of numbers separated by spaces. We split them into individual words. We convert each of those words into floats and append them to our numbers list. And then we're sorting that list. So this list, notice we didn't save that anywhere. We just said numbers.sort. All of a sudden we got 2, 5, 7, 12, 21, 75. Horrible handwriting. All right. So then we're saying, hey, what's the midpoint? I got 6 of these things. If I divide that by 2, integer math, going to get me 3, right? If len numbers modulus 2 is equal to 1, which if I did that, right, I'm going to get 1. Print numbers midpoint. Print the third one. 0, 1, 2, 3. Those are my indexes. So I'm going to print out 12. This one has to do with when it's even. If I'm right here, if my midpoint doesn't point at 1, then I've got to move it up 1. So it's actually going to move up and divide by 2, and it's going to end up printing out 12 at the same. Or if I had, 85. It's going to end up printing up 12 if the number is larger. Confusing slide, but this is one that you should play with. And while you're doing that, you could actually work with your debugger, which we're going to talk about here at the end in just a second. Okay, all this list stuff, all this changing list, adding things to list, modifying lists. Lists are mutable. They can change as much as you want them to. On the other hand, we need something that doesn't change. Think days of the week, or months, or values of money. Those are things that don't change. What's the big difference between a list and a tuple? A tuple uses a parentheses. If you have a list of things separated by commas inside of parentheses and you assign that to something, you have created a non-changeable list, and that list is called a tuple. And tuples are awesome because they can become the anchor of your program. Think bin numbers and bin locations in an Amazon warehouse. You don't change those very often. They're static, and they need to stay static for a long time. You don't want to put that in the list because some Yahoo can start inserting bins and removing bins and stuff disappears like entire computers and trucks, and it's awful. Tuples. It's a Python structure that's immutable. You can't change it. You can't. All right. Now, what you can do is you can create new ones. Notice we got fruits. And if I dump out fruits, how do we know it's a tuple? It's got parentheses around it. I've got meats, which I created. Dump out meats, parentheses. There we go. I can create a new one. I can't change meats or fruits, but I could add meats and fruits together to create a food. Meats first, fruits second. Veggies, celery, beans. Notice it's a list, square brackets. I could change this if I wanted to. I use our magic keyword tuple, just like we had a magic keyword to create a list. We have one to create a tuple. All of a sudden it's immutable. Can't add to that list anymore. That's the only veggies we get, celery and beans. Ooh, boring life ahead of there. But you get the idea. Tuples can't change. All right. Really the last, we're getting close to it. We're going to define functions now. So far we've just been putting stuff in a file and it runs, follows from top to bottom, boom, boom, boom. Everything's nice. But that's not the way you normally write programs. We want to create little functions that do work for us so that we don't have to repeat code, that we can use the same thing over and over again and just pass it a single line instead of writing 20 lines of code over and over again. Think about one of our menu programs that we've created. We're going to call that menu over and over again. Right now, we've just been putting it in a while and letting it go. But what if we did a menu function and went off and did a bunch of stuff, and we came back and we want to do the menu function again? Do we have to go back to the top of the program and fall back in our loop? No, it's not what you do. You create a function that contains your menu. Call the menu when you want it to print out. Otherwise, move on. But the key to creating a function, very simple. Keyword def. Name of your function, what you're going to have passed into it, inside the parentheses, those are our parameters, colon, very much like our if. This line right here is called a docstring, and it's very important because Python actually reads the first docstring after the keyword def, and that's the help text that's attached to that function. So if you loaded this function, you could type help square after this, and it would dump out this little line right here, returns the square of x. Now you notice the return statement. The return says, hey, we don't do anything here. They pass in x. The very first thing we do is multiply x times x, squares the number, and then return. That's it. All right. You can do it in the Python shell, which we're going to see, and that's what we've been seeing with our triple greater thans all day, but it's more convenient if you put it in an idle window or in a file. Here it is, keyword def. What do you want to call it? No spaces. You can have as many parameters as you want, separated by commas, inside the parentheses, colon, indented body. This function goes on until the indent is broken. Parameters, what you're passing in. What you pass in should match what we're expecting. So in this case, we're expecting one variable called x. We're expecting that you would return a number. All right. My docs string for this would say returns the square of x. X is assumed to be an integer or a real number, so that they don't pass me a string. Just put it in the documentation. Some functions don't have any. We've already seen some of those functions, haven't we? Just back on list, where we said numbers.list, open parentheses, close parentheses. Don't need any parameters. I've already got numbers. Let's sort that thing. The return statement. You put a return statement if you want your function to return something back to who called it. It is not required. If it doesn't retain a return statement, then it transfers back where it came from once all the indented code is done inside of the function. And if it returns nothing, I told you everything returns a value. It actually returns none. It returns the value none. So remember, if you start seeing none in your program, that's probably what you did. You're missing a return statement, or you assigned something the wrong way. None means everything worked great, except that's not what you expected. Here's a good one. Notice the function down on the bottom. Def, it's called odd, takes a single parameter called x. There's the doc string for it. Returns true if x is odd, false otherwise. Then I'm just doing a simple question. If x modulus 2 is equal to 1. In other words, if I divide anything by 2 and the remainder is 1, it's odd. Return true. Else, return false. Whenever I hit this return statement, whether it's here or here, this code goes back where it came from. It leaves. Return throws you out. You don't do anything after that. If we didn't have these return statements, this whole function would execute till we got to here, and then it would go back. But as soon as you hit return, you're done. It's a good little function to remember, by the way. Stuff that you can copy and reuse. So far, when we've run our programs, we've just run them, and they've been happy that they went. But guess what? Most of the time, behind the scenes, Python was creating what's called a main. Main is the entry point for a script. We didn't name it, but it was still there. Now we're going to start naming that. All right, we'll start creating. Here's where I want to start. Here's what I want my main to do, and we'll go from there. Main things have to be defined before you can use them, but the easiest way is create a main, and we'll see how just to do that in just a second, and then call main. Good example right here. Computer square. Remember, normally we just start our program and it falls down. There's our documentation. We're defining main. Okay. We're not running main yet. This def says, hey, create this thing and store it. Okay, so we did. Oh, we got another one called square. Create that thing and store it. And then we're saying, hey, if the name of the program we're in is equal to main, in other words, it is. Remember, main gets created for us behind the scenes. Then let's call main. This calls and goes right up here. Hey, and rather than butcher this slide, I'm going to show you this in Thonny. This is the code we were just talking about. All right, now let me go ahead and clear things out here. And I'm actually going to debug this. Some of you may have hit this button by accident, but this is a great little button. I'm going to debug it. And let's see what happens. Notice it highlights this up here. You got these buttons. This one's step over, step into, step out, and resume. If you hit resume, it's just going to start running. I'm a big step into fan. So if I step into it, hey, it says, oh, that's a doc string. Computes it. Hey, it says, okay, that's the thing. That's the documentation for this file. We define def main. Watch what happens over on the right-hand side when I step into. Notice it got list. It said, hey, this function over here. We haven't executed yet, but it's been defined, and it contains some stuff that we're going to have to get to later. Now we're hung on def square. It's defined. I don't know what's in it, but we'll get to it later. And then we get to this lane right here that says main, open, close. I have one of those. So we're going to go do that. Step into. It says, hey, do I have one of those? Yes, I do. Let's go do that then. The window pops up. All of a sudden, we're in the main function. Keep an eye on these values down here on the bottom. This window, local variables. There's our doc string that prints out what it is. There we go. Okay, first things first. Here's my whole line. I got to do the end part, but hey, the end part's got a parentheses. Look inside there. Oh, it's an input. Okay, the input's got a parentheses. Let's look inside there. There's a string. Oh, good. That's really what I want. Let's pass that string into input. There we go. Look what happened down here on the bottom. There's my prompt. I'm going to put in the number 6. There's 6, and I press enter. Notice how it turned into 6. In other words, we can see our variables as they're occurring. Number, this whole statement over here turns into 6, which gets assigned a number. The variable appears down here. And then I'm going to say, hey, print the square of number is, and I got another call to another function, square number. So let's go do that. Keep going. I'm stepping into. I got the string. String's okay. I got the number. The value of number is 6. I got the string. String's okay. Now I got this thing called square. All right, let's got some parentheses. Let's resolve that first. Number turns into 6. Now I've got square 6. Okay, let's go see what that does. Remember my definition from square way back over here? That's my square. Executing it returns the square of x. There's my docstring. Howdy docstring. Okay, now I got a return statement, but I got parentheses. Let's go resolve that. Oh, look, I've got an x. Oh, that's 6. And then I got another x. That's 6. Cool, they're both numbers. 36. Return 36. Cool. So I do. There's my 36. Print it. Notice how print returned none. Like I told you, everything always returning a value, but most of the time it's none. But look, it did do our print. The square of 6 is 36. Once we keep stepping, main return none. Boom, my program's done. But you can see the variables occur and how we stepped into each of these functions. We define this. Oh, I have one of those. Let's go do that. Started to execute and resolve each of the lines in this code. Oh, it went to square right here. Oh, I have one of those. Let's go do that. Docstring, return, resolve. This turned back into 6, replied back to here. This printed out. I hit the end. It returned back to here. And we had nowhere else to go. We're done. You can use your debugger if your program is behaving badly to go see what's really happening, what it thinks you wrote. And most of the time, you'll get a halfway through a debug and go, that's not what I meant to do. That's not what I meant to see. That's why the stop sign's there. Just stop it, fix your problem, debug it again. Now, by the way, in Thonny, you don't really have a way to set breakpoints easily. All right. But in Spider, you do. You can click over here on this side, click once, and it'll put a red dot by that. And when you can run your code, it'll actually stop when it gets to square. So you can stop and see the state of all these things. But Thonny, usually you're just walking through it one at a time. Okay. Dictionaries. So far we got list, which we can change, append, insert, do all sorts of stuff too. Tuples, we've got a list, but you can't change it. List uses square brackets. That's how you know it's a list. Tuple uses parentheses. That's how you know it's a tuple. Now we got dictionaries. And dictionaries are when you're associating one thing to another thing. Like mammal. Mammals, just like it says, you're putting things in an organized way so that you can look things up. They're called association lists or tables. You're associating a set of keys with a set of data. And they use the squiggly braces. All right, sequence of key value pairs, sometimes they're called entries, in curly braces, and the colon separates a key and its value. Like a look at the phone book there. This is a single entry. The key is Savannah, that string. The value is the phone number. Key, value. Here's a fun one that shows you that we don't really care what type we're dealing with. Name, key, value. Age, value. Notice Molly and 18 are not of the same type. Dictionaries don't care. They care that the keys are findable and unique. So I can't have more than one phone number. I can't have more than one friend called Savannah, or more than one name, or more than one age. Somebody see how that works? Those first ones, the keys need to be unique. These values can be whatever you want them to be, of any type that you want them to be. It just depends what you want to search for. Keys in a dictionary can be any data of any immutable types, things that don't change. Normally strings or integers. So what does that tell you? You can't have a key that's a list because lists change. Can you have a key that's a tuple? Yes, you can, because they are immutable. One of the keys there about how all these things start to get related. All right, if we want to add a new one, then we got to tell it, hey, I give it a key and a value. I created a new dictionary here. I'm giving it a new key called name with a value of Sandy. I'm giving it a new occupation, key called occupation, with a value that contains hacker. So now if I dump this dictionary out, it's going to show me there's my keys, name, occupation. There's my values, Sandy, hacker. See the semicolon separates the two? If I wanted to replace something, I can say, hey, info, go find the key occupation and set the value to be manager. Sandy got promoted. She used to just be a hacker, but now she's a manager. Notice instead of using indexes, we're using our keys to get the things now. And that's kind of rough on some people because we've usually probably spent a year or so teaching you to use indexes till we're blue in the face. But now we've got this data structure called a dictionary that doesn't use indexes. It uses keys. What's inside the square bracket is referencing a key, which is attached to a value. If you want to find out what's in something, you got to use the key, right? So remember in our previous one, we got name and occupation. Those are our keys. Sandy's associated to name, manager's associated to occupation. We come in, we say, hey, what's the name? It says, oh, Sandy. If we come in and we say job, then it goes, horrible death. Because we don't have a key called job. All right. So one of the weaknesses is that you got to know your keys. However, Python does a good way of saying, hey, let's go check for the key. You can use hasKey function. You can just say, hey, if we were talking about our list here, we could say, hey, info.hasKeyName, and it's going to return true or false. And if it's true, we go get it. If it's false, then we do something else. Another way is to use get. This is actually supposed to be get right here. All right, if job and info, print info get job. The get method. I'll show you more examples of that one in a second. Now, the other thing, here's our starting dictionary up on the top. We got two keys, name and occupation. Sandy's associated with name, manager associated with occupation. To delete an entry from a dictionary, you pop it. You just pop it off. Remove its key using the method pop. Because remember, if you don't have a key in a dictionary, you can't get to the value. The value is no longer accessible. All right. When we pass it in, we have a choice. We say, hey, info, pop off anything associated with the job key, and don't give me anything back from that. In other words, I just want it to go away. I don't want to know what it was before. I don't care. Just get rid of it. You send it two parameters, or one. When you send it two, you're saying, hey, give me this key, return this when you're done. Now, what does none do for us? Absolutely nothing. In other words, this one we just wanted to get rid of the job. We're not keeping up with it anymore. Now, if we print it out and pop off occupation, that's going to print off manager. You know, if job wasn't on there, then fine, we got nothing. We're popping it here. We're saying, hey, give me occupation. I know occupation exists. Manager. But you notice what happened to occupation and manager when I did this statement. They went away. Poof. When you do info and dump it out, all that's left is name and Sandy. So you generally want to use get instead of pop if you want your dictionary to stay the same shape, if you want it to maintain its data. If you want to get rid of something and get the value back, do it this way. Pop with one parameter. The cool thing with dictionaries, it does have a way where you can just say, hey, here is my dictionary. Let's do a for loop with some variable called key or my keys or something. And we could do this. Just go get all the keys. And then as you're walking through, take that key, print what the key is, and say, hey, dictionary, use this key and tell me what the value is. So it's going to print out a nice list like this. Grades. All right. Going to print out a nice list of grades. This one, we could say, hey, I've got this dictionary. Let's turn it into a list. Hey, grades dot items. And turn that into a list. Remember what happens with lists? Now we have things that we can actually reference by indexes and walk through. We know we've got 3 of them. Print out the first one, print out the second one, print out the third one. Each of these, this is a list containing tuples. Remember the parentheses? These can't be changed, but this is a list. We could remove things from the list. Another way to do it. For this key and value, every item's going to return you back a key and a value. We gave it a place to store the key, a place to store the value. Now we can just print them out. They're kind of difficult to deal with, but it's a great way to store data quickly without having to write the files or do any other organization. Again, the keys. Remember, we got info, which is a dictionary. Let's get the keys into a list. Now it's a list, right? Use sort. Sort will put it automatically in alphabetical list. And then we can walk through our sorted list and print out the key and the info. In other words, it doesn't matter what order we put it in. You can always turn it into a list and sort it because lists are mutable. They're changeable. Now it's sorted. Walk through it in a sorted way. Dump it out just like we did on the previous 2 slides. Same structure. So this is something that you use all the time where you're flipping back and forth between a dictionary and a list. This is going to give you a list of all the keys, not the values. We're sorting the keys, and then we're pulling them out of the dictionary in a sorted way and dumping them. Info is still not sorted, but the keys are in the list called the keys. Now we got all these operations that we could use, and this is a good slide to kind of keep up with, is 40. When we're dealing with dictionaries, we can ask it how long it is. We can get to a value using a specific key. We can get to a value, we can replace a value, we can add a new one. If this doesn't exist, it's going to get created with whatever value you assigned. If it does, it's going to return the value, or we can set it to a new value. But this is the key. Don't use indexes, use the key. Here's where we can say, hey, get returns this if it exists, returns this if it does not exist, which in most cases is none. You could actually set this to false if you wanted to. Same thing. All right, this is square brackets right here. These square brackets go with this, and they're just there to show you that this is optional. Same here. This section is optional. You don't have to have it, the comma and a default. You can pop things off using a key. You can get a list of keys and save it as a list of values, save it as a list of items, which is going to be a key, comma, value list, tuple that you could use. Delete the whole thing. One line, you can clear out the whole thing. Or you can walk through it one at a time. For a key in the D, go walk through the keys, give them to me one at a time, then we can use those keys to get the value that we want, either this way or that way. All right, quick one. This is a small table, dictionary, that associates base 10 numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, hexadecimal numbers, A, B, C, D, E, F, to their binary equivalent. Quick use of a dictionary. Keep that in mind. So that's our table right there, called hex to binary table. I created this function, def convert. It takes a number and a table, builds and returns the base 2 representation of number. Binary starts out as an empty string. For each digit in number, all right, remember we're getting this string, and you can always walk a string one character at a time. I'm taking that number, right, and sticking it in digit. Inside this for, I'm saying, hey, table, take that first character that we got, which we know is a number, use the key for digit, and return that value. So if they send in 45, first character I'm going to see is 4. I'm going to go find this and return that. I looked for this key. I found that value. There's my key. This turns into the value plus binary. There's nothing in binary, so binary now contains, 0, 1, 1, 1, 1. Sorry, 0. Smiley's getting lost here. 0, 1, 1, 0, 1, 0, 0, space. And going back and forth too fast. There we go. 0, 1, 0, 0. This turns into 0, 1, 0, 0 space. I came in for the next digit. Remember we had 45. 5. Table digit. 5. Turns into, wow, 0, 1, 0, 1. Adds it on there. What was already there. Adds it to the next number. 0, 0, 0. Binary. Return binary. So it converts it for you. Dumps it out like this. But notice, function executes until we're done. Now, the mode of this is another one that you could have used. You might use it on Pride and Prejudice to see what you get out. Input the text, convert its words to uppercase, and add the words to a list. Splits it. It's supposed to be indented. Words append, words upper. Just creates a big list of words. This one is another one. I believe this is in your code for this week. If not, copy this one out and work through it. This one basically counts the occurrence of words inside of a document and prints out at the end the one that happened to the most number of times. This is the coolest code in here because for word and words, in other words, for each word in a line, dictionary, go try to get the word. If you don't find it, put none in number. And then we say, hey, if the number is equal to none, in other words, the word doesn't exist, let's add the word with a value of 1 for the value. Add the key of type word with a value of 1. When we go back, if you do it again and it's not none, then we know that that word already exists and he's incrementing 1. Let's see. Yeah, here we go. If he doesn't find it, add that new key with a value of 1. If he does find it, hey, dictionary, go find that word, which we've already found before, and increment 1. All right. Hey, dictionary, give me this list of values, and what's the biggest one? The dictionary give me a whole list of your values and tell me the max. We store that one out into the maximum. And we're checking to say, hey, go to get the dictionary for each key in the dictionary. Let's go get it and see if that's equal to the number that we found. And if it is, then we print out the mode is key. In other words, that's the word that occurs the most number of times in a book. This is pretty abstract, but it's fun to walk through. This would be a good one. It's called mode.py. Uh, Please let me know if it's not in your chapter 5 stuff, and I will send it to everyone because this one is a good use of it. You can give it any input file, and we already have Pride and Prejudice, which is a pretty large file, and you can watch it happen and debug it a little bit, and then go ahead and press resume to just step to the end, and so that you understand how it works. That's all I've got for today. Remember, we will meet next week, barring weather or COVID, and I hope to see you again.